Originally I drew a 6-membered ring as being flat like that, with that angle as 120 degrees. In fact, a 6-membered ring is not flat, it adopts a chair conformation. This is a chair. Okay, the reason it's a chair is because this molecule, this part here, is supposed to be the back of the chair. This is the little bit you sit on, and this is the little bit you rest your legs on, okay? So can you guys see how that could be, that could kind of look like this chair over here? Maybe on a good day with a following wind. Okay, so here's a little animation which shows you what happens as you rotate the front atom round and round and round, and the little ball goes up and down the curve. You guys like this stuff? It allows you to understand it, right? I love this stuff. I think it's brilliant. I would say maybe a third of you, maybe a quarter of you, forgot to rotate the hydrogen away from you in one of the questions, right? And so there are 4 possible groups, and you have to rotate the lowest priority group away from them.
Right, so here's our phenoxide ion. So we're looking at how this is stabilised through resonance. Okay, so we can draw a pair of curly arrows, one going down there. Now we can't just leave that structure as this, because that represents us forming a new carbon-oxygen double bond, right? Now, this carbon here already has 8 valence electrons, so we can't just draw a structure with a double bond there. We have to remove one of the pairs of electrons that's in another bond to that carbon atom. So we can represent that by a second curly arrow. Let's just start that from the double bond, move into there.
Okay, welcome to this pre-lecture for Chemistry 1018 Organic. This is the first of the pre-lectures that I'm doing in this course, so even though it says pre-lecture 2 at the bottom, that's just because this one comes before lecture 2. Don't worry, you haven't missed anything. As you might be able to guess, we're going to think about what electrons have to do with acidity and basicity. So the first thing we need to learn how to do today is to draw acid-base reactions using curly arrows, because curly arrows are the way that we as organic chemists show electron flow. Now, you've already seen how to use curly arrows. You've seen them how to use them to show the formal movement of electrons between resonance structures. But we can also use curly arrows to describe reactions, and the rules of drawing curly arrows are the same whether we're showing resonance structures or describing reactions. And most importantly, they show the movement of electrons. If you understand that, and put that into practice, your curly arrows will be okay. So, since curly arrows show the movement of electrons, they have to start at an electron pair. So that could be a bond, a negative charge, or a lone pair. And they're going to flow from these electron-rich sites to electron-poor sites. That's just the way electrons are going to want to flow. Let's look at what's happening again using Lewis's definition. Lewis said an acid is a molecule that accepts a pair of electrons, and a base is a molecule that donates a pair of electrons. So here's our base. It's got electrons to donate. It's going to donate them to this acid. By the end of the reaction, the acid, what's left of this acid, has become more electron-rich. It's got a negative charge on it and 3 lone pairs. Whereas the ammonia, which was neutral with a lone pair at the beginning, is now positively charged and hasn't got any lone pairs.
Welcome to our third experiment, the Greener reaction. Here's our basic setup with the retort stand at the back and the magnetic stirrer at the bottom. And here it's with the bosses clamped securely and clamped such that the bosses face upwards. Here we have a detailed view of the boss facing upwards. The next piece of equipment that we're going to need will be the super seal. As we can see now, that is a piece of rubber, a rubber membrane that is put into the other neck of the round bottom flask and folded over the neck, and this way it sits tightly. Final piece of equipment is our nitrogen bubbler, where we have a nitrogen inlet at the bottom and a nitrogen outlet at the top. We put that on top of the reflux condenser, and in this way this whole apparatus setup is sealed airtight. And all that remains is to connect the lines, the water for the reflux condenser and the nitrogen for the nitrogen bubbler. And once that is done, we take the next tube and connect it to the outlet, which is the top of the reflux condenser. And again we have to secure that with a Jubilee clip to make sure that it doesn't fall off while the reflux condension is going on. Once we have connected everything, we adjust the nitrogen flow rate to 1 bubble per second, which helps us flush the whole apparatus with our inert gas atmosphere, which is nitrogen.
First, turn on the spectrometer by holding the power button. On this menu, press 1 to choose standard methods, and then choose 3 to choose the spectrum option. It will then ask you to change your boundary wavelengths. For this example, minimum 280 and maximum 330 nanometers, and we want to record the absorbance. Before taking a spectrum of your sample, you must take a reference, which contains only your solvent. Place your reference cuvette in the holder and press the blue button. Then remove your reference cuvette and replace it with your sample in the holder. This time press the green button. Your spectrum will appear on screen, and you can use the arrows to locate maximum peak absorbances. In this example, the maxima has an absorbance of 1.45.